Okay, so let's start discussion. Some of doubts are there. Let us clear it first, okay, before we move next topic. So let's discuss this doubt from the paper. Question number 41. In a YDSA, distance between these two slits is given, where lambda wavelength, okay, screen distance capital D is given. Central maxima is at O, okay. Find the distance of fourth maxima from O. Fourth maxima, what is the formula? Directly formula for nth maxima, nth order, nth order maxima, nth order maximum formula. Y is equal to n times lambda d by d. So n is 4 lambda d by d. Substitute in the question, they have given the values. Small d is equal to 5 lambda. So 4 lambda, capital D is not given. Let's keep small d is 5 lambda. So 5 lambda is given. Lambda get cancelled. 4 capital D by 5. 4 capital. What is the problem in this? Tell me. No. Mistake key change will be there. Huh. What is the reason? What? 5 lambda. Huh. See, this formula is definitely used. When do we use this formula? Basically, the idea is that this is the d, and we take this angle as theta, and then we take this as this distance we take as d sine theta. That's the part difference. We take theta is very small, then we do approximation. But suppose if you are not doing approximation, then you check. That's also right. You can check that approximation because d sine theta is equal to delta x, okay, and delta x is n lambda, and they are saying as the fourth, so n is 4. Yeah, I think this is one reason this answer will not be there, because we take d sine theta as theta, but here we cannot take. The reason is that this angle is not getting approximation. Why? Because here this delta x is 4 lambda, and here d is given as how much is 5 lambda. So 5 lambda into sine theta. So from here we will cancel out, we will get sine theta as 4 by 5. Yes, that is one of the reason you can say that. Then everything will change. This formula will not work then. So the formula is working. Why? Because sine theta is taken as theta. When is sine theta taken as theta? Sine theta is equal to y by capital D. Right? This is the condition. And when you take sine theta as theta, then only we write this, then only formula comes. So this reason is that because y is very small, but here y is how much? Y is 4 lambda. We cannot directly use this formula, then that formula will not work. Okay, that's what it, that means we have to use then formula for this, that this is theta, this is y, this is capital T, then this becomes root under y square plus d square. Okay, this is what they have given, I think. So anyway, theta is 4 is to 5 now. So this is the this is 4. Then this ratio you will know. This is 4, 5. Then it will become 3. So from here, sine theta is 4 by 5, and we want what? Y we want, na? Y we want. So from this triangle, what is that ratio? Sine theta. Sine theta ratio will be y by 4 sine theta 4 by 5 only, but y by root under y square plus d square. This you need to solve then. But technically, then it is a different question. Okay. Then you need to solve this one. Then you solve this. 16 y square plus d square is equal to 25 y square. So 16 d square is equal to 25 minus 69 y square. Then y becomes 4 by 3t. Okay, that's what it is. Y becomes 4 by 3. No, no, the idea is that sine theta should be written as theta. Sine theta can be written, then only that approximate formula work. Sine theta can be written as theta, then only it will work. Otherwise, it will not work. When can we write sine theta as theta? When can we write sine theta? Sine theta can be written as theta. That means if y is very, very smaller than t. But how do you know y is smaller than? Right now you have to calculate y only, right? Y only. That means you do not know. Initially we will not know anything. So always then use this formula, right? So then means see here y square plus d square, this and this d is almost same. I think this is not going to give proper way. Better you use normal formula. Y is equal to d means delta x. Delta x is equal to part difference. Delta x is d sin theta. And actually this is also not the correct approach, because here we take this is the slit, right? Slit distances we take as this. Here also we make approximation. This is capital D. We take this is almost very, very large. So this distance we take as a small d, and then we are taking this as arc length. So when we take arc length is, I think this approach is okay. We take this as arc length. This is theta, very, very small angle theta. This is the y value of y from this. Okay. So d sin theta is the path difference. I think this is where most of the students might have made mistake. This is the formula. During formula they should tell that. Why should we use that formula? Correct. If they tell only, then only we can solve. Otherwise we will not, because many people will take that answer. Hmm? So they will start writing this d small d as very small angle into theta. So then this they will write as theta is equal to y by capital D. Right? So what it is. Okay. So this would I think mention in the question. This D has been given as very, very small. D always is small, na? D is always very, very small. Correct, na? D is always very, very small in this formula. But how do we student know about this now? No, students will not be able to know unless you have to use the exact formula only. That means in all the cases you have to use exact formula. Exact formula only use then in all the problems. D sin theta as the part difference you use always. Delta x you use d sin theta. Whether sin theta will be theta or not, that will come after calculation. That is what is the mistake. Right? Then they should not tell this at them. They have to tell that if theta is very small, if theta is very small, then only we can go for this. Otherwise, we cannot go. But how do we know theta is very small? That is also problem. Yes. See, I think there now you need to first of all solve. Suppose you take, for example, suppose you take calculation of sine theta you do. Okay, calculation of sine theta you do. So suppose for delta x is n lambda, and delta x if I put as d sine theta as n lambda for maxima condition, then Sin theta will come as n lambda by small d. Okay. Now I think here is where many problems are coming, right? Main problem is coming here only. So d should not be in terms of lambda, like 3 lambda, 4 lambda. D must be much larger than n lambda. That is the condition you can do. Okay. If d small d is much larger than n lambda, then only sine theta can be written as theta. Okay. I think this condition they need to tell that. But here D they have given us 5 lambda and this is 4 lambda. So this has come as 4 by 5. This is where problem is happening. 4 by 5 is nearly 0.8, right? 0.8 it is. It is not very small. Very small means it is not going to give. Very small means it should come nearly 0. If it is coming, let us say 0.00000001 like that, then you can write sine theta as theta, because sine theta is very small, theta is very small, right? Yeah, so that means before using the formula, you check about this condition. This condition you check. You have to check this condition. Whether D is D and lambda you compare. I think you compare D and lambda. You compare D and lambda. D and lambda comparison you have to do. So if D is almost, let us say, 1000 times larger than lambda, 100 times larger than lambda, then you can use sine theta as theta. Otherwise, we should not use it. Okay. Okay. Then let us go to the next question. Uh, Next question is what? Okay. 45 is also there. No. Next 21. Huh? 21. Consider diffraction pattern obtained on sunlight incident on a pinhole of diameter 0.1 micrometer. The diameter of the pinhole is slightly increased. It will affect the diffraction pattern such that pinhole means it is circular or what? Might be like a circular they are giving us. Slit generally we don't take circulars. We take anyway, but see, in case of YDSC, we have seen there is a white light also difference in YDSC. We have seen that. If single slit experiment, it should not happen, but if it is a monochromatic, it will happen. But white light, you can assume it is made up of so many white, I mean, so many colors. So each color can produce its own pattern. Each color will produce its pattern, but the problem is that they will be overlap and you will not be able to identify that. Okay. So what he's saying is this size decreases, intensity decreases, size increases. What is it? Will affect the diffraction pattern such that its size decreases and intensity decreases. Size decreases, intensity increases. Size increases, intensity decreases. Size decreases. Which size and what intensity? Size means this size. This size means, let us say this size is B. It is like a slit only you take. And then if you see here pattern, let us say monochromatic it is. For monochromatic it is like this way. Right? And central bright, if they are talking of central bright, this is the radius of that, and that radius is lambda d by b, right? Radius of the central bright. But what are they asking? If the diameter of pinhole is slightly increased, diameter means this b. B if you increase, it will affect diffraction pattern such that its size decreases. I think size means might be they are talking about the central bright. Might be they are talking about this radius. So if this radius or size, if you increase b here, suppose you increase b here, then this will decrease. So size will decrease. That is one possibility. Size can decrease. But what about intensity? Intensity. Okay. What about the intensity of the pattern form? that you need to think about. What about the which intensity means what intensity they are talking about, which color intensity will affect the reflection pattern such that, suppose if you take monochromatic, let us say monochromatic, so you know on what factor the intensity depends, this intensity of the uh, how does this intensity depends on B? Do you remember how does the intensity depends on B? Let us talk about that intensity. Central maxima intensity formula is what? Remember, central maxima intensity formula is I naught. Central maxima intensity formula is I naught sine uh, what is that, n delta phi by B. I think this is how this and n delta phi by B whole square, right? Is this correct? Yes. Sam, remember that formula. Tell me, is this formula correct? We have derived it also. I don't exactly remember, but I think somewhere like this only we have derived it. Phase difference. Or by two it was. Was it by two was there or what? I don't remember exactly. Just check that. Was it by two? Might be. I think this was two here. I think. So where this delta phi due to each phase difference, which was v by 2 sine of theta, b by n. Sorry, this was b by n sine theta, which was y by capital D. I think this is what it was. So delta phi by 2. Yes, Sam, do you remember that? Is correct? And delta phi by 2. So n delta phi by 2. That terms becomes by 2t. I think this is what it is. By 2t. Okay. So for each maxima, I think this remains same, and b factor which is going to increase here. So as this increases, this keep on decreasing. So I think this intensity of central maxima is inversely proportional to this b square. Okay. So if you are going to increase this, then intensity will also decrease. Okay. So intensity will decrease and size will both will decrease. Huh? Both should decrease. Did they give that answer? What is the answer for this? Okay. Size is decreasing and intensity is increasing. No, no. If you take monochromatic, this is the result. For many light coming, what can you say that? For many light, each light will produce its interference pattern. So intensity, what do you talk about intensity then? Intensity generally we are talking for single only, monochromatic. This is the rule. Okay. Hmm. Yes, monochromatic only. No, no, even they give now for many light like white light interference are there in NCRT. But for white light, even if they give, we need to take based on monochromatic only. But separate patterns we can form. We can make separate patterns. Okay. So if they are saying that we have to see effect of B, so suppose white color means white means all the different colors are there, red, violet, indigo, blue, green, yellow, orange, red. So all the intensity will be forming a central maxima. Central maxima will be like this. Okay. Different colors you can take. Some colors may have little bit radiuses may change, right? Because for different colors lambda is different, so radiuses may change. But B, effect of B will be what? Effect of B will be, if you B increase, this radius will decrease, spot side will decrease. Okay. Then coming for intensity calculation, intensity of each maxima, you think about it. Let us say intensity, you are thinking about different colors. So each color intensity of maxima will be this only. Right, for each color maxima intensity. So here the effect of central maxima we are seeing. The central maxima means B is going to increase, means central maxima intensity will decrease. It doesn't matter which color it is. So B, if you are increasing, it must be decreasing only. That's what will happen. Okay. So they need to change this key. Okay. They, they need to change, both should be decreasing. How they will increase? They are talking of central maxima only now, because it will affect the diffraction pattern such that size increases. The diffraction pattern means they are talking of central bright fringe or central bright spot. Okay, so central bright spot, if you take, this is what it is, central bright spot. Okay, for any color you take, they are overlapping. Different colors are overlapping, but the effect of increase of B is, it is going to, if you increase B, then intensity for each color will be decreasing. So overall intensity should also decrease. So both should be decreasing only. It should not be increasing. Okay, right. If any other things are involved, then we are not sure. For any other things, that is not sure. Okay, which is not part of syllabus then. Okay. Then let us go next. Question number 43. Consider three waves represented by equations. This is the resultant amplitude of this. Everything is same. Okay, just draw the vectors. So first is, let us say 3. This is 3. Next vector 4, but angle is 2 pi by 3 means 120 degree. So it will come like this angle, right? Plus 2 pi means this angle is 120 degree. Next 5, 4 pi by 3 means next again to 40 degree, that means here it will be, this will be 5 then. Okay, this resultant they are asking you to calculate 3, 4, 5, and this angle is extra 120 degree, because 4 pi by 3 means that only. Okay, so resultant they are asking, what is the resultant of this? Calculate resultant amplitude. How to calculate these three vectors? You can think of resolving them along x, y, z. And what are the options? Are they asking only amplitude? Only amplitude they are asking. Then you calculate, resolve this. Okay, resolve this. So if you take this as x-axis, negative x-axis, this is 120. This means 60 degree it will be. So this 4 you resolve this side. 4 cos 60 means 2, and 4 sin 60 means 4 root 3 by 2. 2 root 3 will be there. Okay, then this 5 also you resolve. This 5 is making 120 degree from here, and this is making 60, so this will be making 60 only. So resolve 5. So 5 cos 60 means 5 by 2 it will be, and 5 6 sin 60 means 5 root 3 by 2. Okay, now calculate total components along x and y. You complete. So this is 2 plus 5 by 2. 5 by 2 is 2.5, and 2 plus 2.5 is 4.5. So along this 4.5 comes, along this 3 comes, right? And here 2 root 3 is coming, here 5 root 3 by 2 is coming. So definitely this is larger, because this is 2.5 root 3 by 2. So here you will be getting root 3 by 2, right? Okay, so now calculate total. So this is 4.5 and 3, so subtract this, so you will get 1.5. That means you will get 3 by 2, correct? And you are getting this as root 3 by 2. Now you solve resultant of this, right? Resultant is the diagonal of this. So final resultant amplitude will come root under root 3 by 2 whole square plus 3 by 2 whole square. Solve this one. 2 will anyway come out. Root 3 square means 3. 3 square means 9. 9 plus 3, 12. 12 by 2. 12 means 4 into 4 into 3, 2 will come. So root 3 is going to come. That's the answer. Root 3, check answer. This is vector calculus. Okay, any other doubts you have asked? You can tell to Kevin. Kevin will send. Kevin send those questions. Sent. Okay. Question number 40. Two slits, two Young slits. Young's double slit experiment have width ratio 2:3. Two slits ratio. Okay. Then the ratio of maximum to minimum intensity interference pattern is. Suppose one slit's width is B1, another is width B2. This ratio is 2 by 3. Okay. Then the ratio of maximum to minimum intensity is. So in YDSC we know slit width is proportional to intensity ratio. So this is ratio of intensity. Okay. And what is the formula for maximum intensity and minimum intensity ratio? Right, maximum to minimum intensity ratio. So this is I1 plus I2, sorry, root I1 plus root I2 by root I1 minus root I2 whole square. Okay. So now you solve it. This ratio is 2:3 now. So that means you can take root of 2 root 3. Maybe you can just divide with, sorry, this is I2. So divide it with root I2. So if I divide it, become root under I1 plus I2 plus 1, root under I1 by I2 minus 1. Solve it. So this will become root 2 by 3 plus 1. This will become root 2 by 3 minus 1. Now you solve it. Just solve it and match with the option. Solve it and match with the answer. You can take LCM also to simplify. I think root 3 is larger now. So you can take root 3 plus root 2 by root 3 minus root 2 whole square. Just check with the option which is matching. I think you have to open up in the numerator denominator. Shall we open or shall we rationalize it? I think what they are saying 5 plus 2 root 2. Maybe open it a square plus b square. You do in the numerator denominator. So a square plus b square 3 plus 2 5 plus 2ab 2 root 6. A square plus b square here also 5 minus 2 root 6. Right? That you check. Option second is coming, right? Okay. Calculation on this. And, hmm, tell me. Any doubt? They have not updated for kinetic. They have only periodic test, I think. Periodic test they have informed you. No, for 11th it is periodic test. Because they will not, they have not updated. They will update it. Next test, huh? No, no, next week. Next week you have a polarization and then this upcoming topic, dual nature, full chapter. Then Newton's laws of motion. Those things. Okay. No, no, this question. Maximum 8 9 questions. Polarizations, then dual nature and Newton's laws of motion. No, no, only polarization. Already this topic is covered now, so we will not take reflection and distance. Reflection already over now. Hmm. Physics, you ask in your class, you just check with sir. They will tell you for NEET. But I think the same syllabus will be there for NEET and JEE. Ah, maybe that is complicated. Done? Any other doubts? Okay, so we have done with this chapter. So what else? Any conceptual doubts in this chapter? We can wind up this. Then next chapter we can go for dual nature. No, no, you need to work out many problem, at least 100, 200 questions when you work, then only you will have doubts. All NCRT questions, all the PYQs, all the difficult level of questions when you work, then only. Without solving questions, then not clear. Which question it is in the test paper? Huh? Which question can you send me? 20. Kavin, okay, Kavin send me that question. In YDS, shift range width beta are produced on a screen kept at a distance of 1 meter from the plane of state. When the screen is moved away, so YDSC, two slits are there. This is the distance, capital D of the screen. This distance is D. When screen is moved away by some change is there in the D. Of course, D is 1 meter and this is 5 into 10 that means 5 centimeter you can say, isn't it? 5 centimeter it is, because if you convert meter into that, it is 5 centimeter. Then fringe width changes by some factor. Okay, changes by the separation between these slits is, so small d is given, the wavelength of light is. So first of all, what are the things given? Let us write that d they have given 1 meter and capital D they are changing it. capital D means this distance, capital the change of capital D is 5 centimeter basically, or 5 into 10 to the power minus 2 meters. When the screen is moved away, this right, fringe width changes by delta beta. Change of fringe width is also given, right? 3 into 10 to the power minus 5 meters. Okay. Separation between the slits, small d is given 1 into 10 to the power minus 3 meters. Okay. Right. Then wavelength lambda they are asking to calculate. Lambda they are asking to calculate. So what are the things given? D is given, delta D is given, delta beta is given, D is given. So first of all, the change delta B. Why beta is changing? What is the formula for beta? Lambda D by D. So what is changing? Capital D changing, right? Because of capital D changing, beta also changes, right? So direct we can say that beta is directly proportional to capital D because lambda and small d are not changing here. So we can clearly say that delta B will change because of change of this. So delta B is nothing but lambda by small d into delta D. This directly we can write it, right? This we can write it because delta beta is lambda by d into delta of capital D. This is like change, right? So now I think we can substitute here because they have given delta D, they have given delta. Direct substitution it is from here, right? So lambda is equal to delta beta by delta D into small d. Just multiplication and division only we have to do it. Okay. So take the ratio then. This by this ratio if you take, then it is going to be 3 into 10 to the power minus 2. This ratio, right? 3 into 10 to the power minus 2. And small d they have given, sorry, this by this, no, delta beta by this. So 3, no, you take the ratio. So 3 into 10 to the power minus 5 by 5 into 10 to the power minus 2 into 10 small d you take 1 into 10 to the power minus 3. Now you calculate wavelength. So this is coming as 3 by 5 and this becomes 10 to the power minus 6. Okay. So you can take factor extra factor 30, so 10 to the power. So 6 into 10 to the power minus 7 you can take. Okay. Check out this answer. Meters it is. So in nanometers, 600 nanometer you can take. So calculation is nothing big. Here the thing is that we should know this formula. Then change of beta means lambda by d into change of capital delta. That's what it is. Okay, any other notes? So the thing is that if you daily work out problems, then you can daily ask doubts and clear it. So you should solve continuously. So many questions daily you need to work out. As a NEET student, daily you have to solve 50, 60 questions. Particularly for physics, you have to give more time. Other subjects are not that much tough. But physics requires concept, problem solving, so much. Somehow we have to do it. Okay. Uh, Give priority to physics, and that's why whenever in class you can come and ask any doubts. Hmm. Then should we go next? I also plan to take up the question, but the thing is that I have to cover up the topics also. So I plan to take questions PPT and want to discuss it. Last time I tried, but time was not there. I could not do so many things. So let us start then next. Dual nature we can start, right? Dual nature. We can start dual nature. That will be better. So still we have time. We can work out dual nature. Whatever time we have, dual nature we can start. And dual nature, there will be many formulas, concept will be there. Formulas also will be there, lot of formulas will be there. So we need to cover all that. Okay. So dual nature. Hmm. Let's start with dual nature then. Okay. Let us start this topic and maybe 1 2 classes we can finish it. Let's start dual nature. Dual nature of matter and radiation. Radiation means electromagnetic wave here. That's what is radiation. Okay. So dual nature, what is meant by single nature and dual nature, that we need to understand first. So first of all, what is matter or particle? Okay, matter means particle here. Particle means it's a point mass of course, but matter is can be made up of many point masses. Okay, but generally when we say matter means we say it's a particle nature. Particle nature. Matter has particle nature. And wave wave means wave has particular kind of nature, that is called wave nature. So let us first understand what is meant by particle nature and wave nature. These two types of nature we have to understand, because in this chapter we will be seeing that light has these two kinds of nature. So particle nature means what? Particle nature means it will have mass, it will have position, it will have momentum. If it is moving, it will have kinetic energy due to motion. Due to motion, it will have kinetic, and also momentum will also be due to motion. If it is moving, then it will have momentum, right? So mass, position, momentum, velocity also we can say, acceleration also we can say. All these things will be defined for particles, okay, or matters, right? So that's what it is. And here first important thing is that it will be a localized thing. Localized means at a given instant it will have only one position. It cannot be having more than one position at the same time. Okay. For example, if one object is here, at this time it has to be here only. I can move this object. Suppose this is object and I move it. After some time its position can change, right? But at a particular instant of time it is only at a given position. That is what is particle. Okay? Particle or matter will have a particular position at a given instant of time, right? It cannot be present simultaneously at more than one point. It is like not like a quantum mechanics or quantum physics. Quantum physics is totally different branch. Where object may be present at more than one means place. That's a totally different idea of physics. So, okay, that we are not discussing. Localization or localized means at a given instant, at a given instant, at a given instant, it is present at a given at a single position. Okay. Then what about wave? What is wave? Wave is nothing but energy in transit. Energy in transit. Energy in transit means energy is propagated using waves, and waves are created due to some sort of disturbances. So waves, what are the important characteristics of wave? Wave has a speed called wave speed. Wave has a wavelength. Wavelength. Wave has frequency. Frequency. Wave has amplitude. Amplitude. Wave has phase. Phase. Wave has intensity. Right? These are some of the idea behind waves. Waves has all these features. And then the phenomena wise also you can say what are the wave phenomena, already you discussed in previous chapter. So wave phenomena, you know, wave phenomena. Wave phenomena means reflection, refraction, superposition, superposition, which can be either interference or diffraction. Both are superposition only. Interference and diffraction, both are superposition. Okay. Then many formulas, means many phenomena will be there. Interference, diffraction, what else? Polarization, particularly for electromagnetic waves, right? All those phenomena of wave which we know, right? Particle, what are particle phenomena? Particle phenomena means what? Particle can um, particle can hit other particles. Particles can collide. Particles can collide. There can be particles can collide. There can be momentum exchange or momentum change, or they can exert force. Right? These things we know about that. Particles. Basically, you can say the Newton's classical physics you can apply here. Classical physics or Newton's mechanics you can apply. Classical physics. Okay. Particles. Any idea behind particle means they will follow Newton's laws of mechanics. Everything about Newton's law, starting from uh, first law, second law, third law, the collisions law, and so many things. Okay. Right, so this is the whole brief idea about what is particle nature and wave nature, and they are fundamentally different. Wave is not localized. For example, suppose if I am speaking and electromagnetic waves are transmitting at the same time, waves are reaching many places. Same time, it is present at many places, right? Same time. That's completely different idea. It cannot be particle. Particle has to be localized, but wave can be delocalized. Wave can be simultaneously present at different places, maybe with different intensities or maybe with same intensities, right? So wave and particle are fundamentally different nature. We cannot say that there is a relationship between them. They are completely different nature. But in this chapter, you are going to see that particle which have normally the particle nature, they can also behave as a wave. They can also behave as a wave, and a wave which has wave nature. Wave, which wave? Electromagnetic wave. This we have to note from the very beginning. We are talking of electromagnetic wave. We are not talking of any other kind of wave in this chapter. So when we say that wave can behave as a particle, means we are talking of electromagnetic wave. And when we say that the particle behaves as a wave, means which wave? Not electromagnetic wave. That is what you have to understand. When when particle behave as a wave, that wave is a different kind of wave altogether. That is called matter waves, which is given by de Broglie equation. Okay. And when we say the wave behaves as a particle, we are saying the electromagnetic waves are photons. Photons is what is particle nature of waves, electromagnetic waves. Okay. So this thing has to be very clear in the beginning, so confusion should not happen. Okay. So when we say that radiation, which means electromagnetic wave, has particle nature, particle nature, We say that electromagnetic wave has particle nature, means electromagnetic behaves as a particle. That means we are talking of only electromagnetic, no other, not the sound wave we are talking, not that any string waves we are talking. We are only talking of electromagnetic wave. That means light or any other infrared radiations, gamma radiation, any radiation you take, they will behave as a particle. Another idea what we are talking here is that particles means objects or matter. Matter has wave nature. Matter has wave nature means this wave nature we are not calling them as a whatever the wave which we know, it is a totally different kind of wave. So this wave what we are calling is called matter waves. Matter waves. So that means matter means any object which has mass that can behave like a wave. Which kind of wave? We do not know. We don't have any idea of what is matter wave, but we know it's kind of a wave. That's all. That means we can say something related to the wave nature. That means we can say that, for example, suppose I am talking of electrons. Electron is a particle anyway, we know that. But electron can have wave nature. That means electron can have superpositions. Electron can have diffractions. Electron can have some intensities. We are talking in that way. So we say that it has some wave nature, right? Because it is showing some wave characteristics. That is what it is. Clear? That is the idea behind it. Yes? Understood this. Okay, so then we can go detail into that. Then we can go into detail. That means particle anyway behaves like a particle, but it can also behave like a wave. And wave, which is electromagnetic wave, they behaves as a wave always, but in some conditions they can also behave as a particle. Right? So that means particle or matter as well as electromagnetic wave, they have dual nature. They do not behave only as one type. They can behave as two types. Right? That is what is dual nature of this chapter. Okay, so let us first of all understand what is this de Broglie wave equation. De Broglie wave, de Broglie equation, just de Broglie equation. Okay, de Broglie equation. So de Broglie equation you have already studied. So let us consider that if we talk about wavelength, lambda is equal to h by p. This formula, what does this formula means? Okay, so if suppose we are talking of particles here, particles, particularly we are taking subatomic particles, subatomic, subatomic particles, subatomic particles like electron, proton, etc. Okay, so these particles has momentum, right? P is the momentum of those particles. P is the momentum of these particles, momentum. Okay, what is wavelength lambda here? Lambda is wavelength of matter wave, wavelength of matter waves associated with particles, associated with particles. So when we say that electron becomes like a wave, we do not say like that. We say that electron has some wave character associated with it, and the matter wave, lambda wavelength of that matter wave associated with electron is given by this formula. Okay, lambda is equal to h by p. That's what we can say. And now this formula can be transformed into various things. H is Planck's constant. You know that already. H is Planck's constant. Planck's constant. Planck's constant is 6.63 into 10 to the power minus 34 joules second. Okay, this is Planck's constant. Now here we can convert this formula in terms of various other things. Momentum can be written as uh, root under 2 times mass into kinetic energy. Right? We can write this wavelength in this form. Also, if the particle is a charged particle, we should know about the charged particle. So, if there is a charged particle having charge q and it is accelerated with a voltage difference of delta v, Delta V is the accelerating voltage. Accelerating voltage. So you know the kinetic energy of the charged particle. Suppose initially it is at rest. Initial velocity is 0. Finally it has a velocity v. So it will gain a kinetic energy. So that initial kinetic energy is anyway 0, right? So the gain of kinetic energy is equal to charge into accelerating voltage, capital V. So this formula for lambda can also be written as h by root 102 times mass. Kinetic energy is charge into delta V. Delta V is accelerating voltage. So the same formula can be written in various manner. Okay, that is what you need to note. Same formula can be written in various ways. So now let us write some shortcuts for this formula. So I am going to write some formula shortcuts, okay, which you have to remember and solve problems using that. Okay. So let's write for electron or proton. This formula will work for them, for electron proton particles. Lambda can be written in terms of this particle. Let us take electron, it is only first electron, let us take electron. So if you take electron, wavelength in angstrom can be written as root under 150 divided by accelerating voltage V. V they will give, right? We can substitute, we can use this formula. Okay, so suppose if they say that electron is accelerated by if you want, you can write it delta V because this is the accelerating voltage. They will give this accelerating voltage, substitute, because you know H is constant, mass of electron is constant, charge of electron is constant. So delta V they will give, and you can substitute directly and you will get the wavelength in uh, wavelength you will get in angstrom. Okay. Or sometimes if they give kinetic energy, then you can also substitute. Okay. Right. So sometimes if they give kinetic energy, you can substitute. No. I think here this voltage lambda in angstrom also you need to substitute in the same 150 by kinetic energy. Kinetic energy you have to keep in electron volt. Okay. This will be an electron volt, you need to substitute. Okay. I think here electron is multiplied in this voltage because this voltage will be given E into delta V. So delta V you need to substitute here. This E into delta V, that is what is kinetic energy. You can just substitute the values of that. Okay, so same formula it is. After doing calculation, you will get the same thing. Then what else? And if you put further, you put it, you may also get it uh, in angstrom. You can get nearly 12.27. 12.27 divided by root of voltage or root of electron to delta V. Delta V they will give, you substitute it here. But see, I think you do not have to calculate this E here. Means whatever voltage you will do calculation, that voltage will come. This value you need to substitute. This value of the voltage we need to substitute here. Okay. This voltage they will give, that voltage you substitute. Here kinetic energy will give in electron volt, that you substitute. E you don't put it here. Similarly here E you don't put. This will be the angstrom only. What about proton? This about electron I told, all this formula for electron I showed. What about for proton? For proton also note, proton little bit changes will be happening. Because of mass of proton, lambda will become 0.286 by root of accelerating voltage. Okay, in volt. Lambda in angstrom. In angstrom you calculate. Okay. What about deuteron? Deuteron and other things you can calculate. Deuteron. Deuteron wavelength you calculate as 0.202 by root of accelerating voltage. Again, it is in angstrom only. After substituting everything you got. Okay. After you substitute everything, then you get. For alpha particle wavelength will be 0.101 root of accelerating voltage. Okay. So this is for alpha particle, this is for deuteron, this is for proton, and previously what I have written, this is for all electrons only. All these formulas are for electrons. Better you can remember this. This is electron, this is proton, then deuteron, then alpha particles. Otherwise, you have to do the calculation from the very beginning. That is what it is. Very beginning calculation, you can avoid it. Particularly neat, you can avoid it. Okay. Then let's go next. What about electromagnetic waves? Electromagnetic waves, let us write for electromagnetic waves. Lambda is angstrom. For everything it is in angstrom. Now you write for electromagnetic waves. For electromagnetic waves, we already know the formula for photons, right? This is the photon energy. Photon energy is equal to h into frequency, which can be written as hc by lambda. Now you can substitute the values and we can calculate the energies. So let us write the formula for energy in electron volt. So energy in electron volt 12375 by wavelength in angstrom. In angstrom. In angstrom. Wavelength you have to put in. Suppose you want to little bit approximate it, you can write 12400. This is little bit approximation, okay? Not much, but it will also give you correct values. So energy of photon, this is energy of photon formula in electron volt, little bit approximation. Okay. And if you want in nanometers, so lambda, if you want nanometer, energy in electron volt only. So 1240 by lambda in nanometers. Okay. So that will be the formula for energy. Generally wavelength they may give in nanometers, so you substitute it here and calculate. This is formula for photon energy. So I think other things from, so questions of radiation pressure will also come in this chapter. Okay, radiation pressure calculation, momentum exchange due to photons getting collide with some surface. Okay, so those things will be there. Then next, so I think here you need to learn about the photon theory of light given by Einstein. Einstein photon theory I will explain. Then okay, so let us discuss about Einstein photon theory of light. Photon theory of light. Okay, so first Einstein has given during photoelectric effect when he discovered photoelectric effect. First point is a photon travels with travels at a speed equal to c, which is nearly 3 into 10 to the power 8 meters per second. Okay, in vacuum, in vacuum, and it is independent, independent of the frame, of the frame of reference of the observer, observer. That means, suppose generally what happens, suppose if there is an observer, an observer is in motion with a velocity v1, let us say, and he is studying some object which is moving with velocity v2. So according to it, he will see the relative velocity, right? He will study velocity of 2 with respect to 1, that is v2 minus v1. That is called relative velocity. But in case of light, that means we are considering as photon. Suppose we are talking of photon. So photon is going with a velocity which is equal to speed of light. So this velocity can be studied from any frame of reference. It doesn't matter, because the observer can be in any frame and he can study. This will be not changing even if observer is moving with some velocity, and that is the basis of Einstein theory of relativity. Einstein theory of relativity is actually based on this idea that with respect to this frame of reference, the light does not change. Light velocity does not change. Okay, that's what light, we cannot say actually it's a particle, although we can consider them as a particle, as photon, but they do not behave like photon. Okay, right. So this velocity of photon with respect to observer, observer is always going to remain c only. Okay, assuming that it is in vacuum, light is moving in vacuum, let us say photon in vacuum, photon is moving in vacuum. Okay, so this velocity of photon with respect to observer will never, that means observer motion does not affect the photon velocity. That is the main idea. Okay, let us go into the next point, point number 2, photon theory. Point number 2, the mass of photon is not defined. The mass of photon, mass of photon is not defined, not defined in in the sense of, in the sense of Newtonian mechanics. Newtonian mechanics. So as Newton has defined this mass of object, it is not defined as an object mass. Okay, so we simply say that, so mass will not be defined. Okay, but we say that the rest mass of photon, rest mass of photon is 0. Okay, so the concept of mass is not defined. The concept of mass is not applicable for photon because photon is not a particle. If it is a particle, then we can apply that, but it is not a particle. Okay. But we can say that rest mass of photon is 0. Next, another thing, many contradictory idea will come. Okay, so you should clearly understand this theory, what the theory is. Each photon, each photon has a definite energy, definite energy and a definite linear momentum, definite linear momentum. Okay, definite momentum. Next, point number 4, the energy E and P. E is the energy of photon energy of photon. P is the momentum of photon. Okay. So this we can write that formula already is equal to h into frequency, right? And P is given as the de Broglie equation h by lambda, because lambda is h by p, right? Lambda is h by p. So P is equal to h by lambda. This lambda is what? Lambda is the wavelength of electromagnetic wave. Wavelength of electromagnetic wave. So from here we can also get a relation that because P is equal to h by lambda, we can multiply frequency in the numerator and denominator. So h into frequency become energy of photon, lambda into frequency become speed of photon or speed of wave basically. So this is the speed of electromagnetic waves, right? So you will say that what about this P is the momentum? Momentum we can say, can we not say about mass? No, we cannot define mass. So we should not try to calculate the concept of mass for photons. Okay, right. Then next, other things. Okay, this Planck's constant H, which we are talking about, 6.6, actual value is 6.626 into 10 to the power minus 34 joules second. It can also be written in terms of electron volt second as 4.136 into 10 to the power minus 15 electron volt second. Okay, sometime we can use this. So here you note one point that all the photons, all the photons of the light of a particular wavelength, of a particular wavelength have the same energy. E is equal to hc by lambda or h into frequency. That's the same thing, right? Next point, point number 5, right? Point number 5. These points I am writing from uh, SC Verma, but very important, very important. This is other textbook they may not have given that much clarity. A photon, a photon may collide, a photon may collide with a material particle, with a material particle. There are a lot of questions of collision of a photon with particle. The total energy, the total energy and total momentum and total momentum, total energy and total momentum remain conserved, remain conserved in such a collision. So whenever collision happen, total energy and total momentum must remain conserved. That means it will follow the Newton's laws. Okay, but the photon may get absorbed. This is very important point. But the may get photon may get absorbed and or a new photon may be emitted, may be emitted. Okay. So we can clearly say that thus the number of photons may not be conserved, may not be conserved. Number of photon will not be conserved. Other things, It may be conserved also, but it may not be. We cannot say sure about that. Okay, point number 6. This is the most important point. Point number 6. Put a star marks for this. This point is the most important point of this chapter. This whole chapter, people will get confused initially. I was also confused because things are not given clearly in the textbook. Only after reading S.C. Verma, it comes to a proper understanding about what is the meaning of intensity. Okay, because I was also giving some argument before, but that was not clear when I read further details. Okay, so note about this. Intensity of light of a given wavelength is increased intensity if intensity of a light intensity of a light of given wavelength given wavelength lambda is increased is increased given wavelength is increased, there is an increase in the number of photons crossing a given area in a given time. Okay, so the energy of each photon remains same. This is very important. The energy of each photon remains the same. Energy of each photon remains the same. Now I will explain about the meaning of intensity, which is very important. What is the meaning of intensity? Meaning of intensity of light in this chapter. What is the meaning of intensity of light in this chapter? This meaning of intensity is fundamentally different from all previous chapter intensity. This is the particle concept. This is the particle concept. Light is behaving like a particle. So note the formula for intensity. Intensity I is total energy, number of photons into E by time by area. So you know this term is also called power. Power is equal to N into E by T. This is also called power. So that is what it is. It is power by area. That is what is intensity. So here note that intensity is going to be defined as proportional to N by T. Now you may say that energy of photon can also change, when intensity can also change. No, here intensity does not depend on energy. You can see this formula, it is depending on energy. But in this chapter, the term intensity of light, which I am writing here. Now let me write another definition of intensity, that is called photon flux. So photon flux or intensity of photons, intensity of photons. It is the number of photons per second per unit area. Here in this definition of intensity, the energy itself does not come. You see in this definition, the factor E itself is disappearing in this definition, right? Are you getting this? So this is what is where lot of confusion is there. Many teachers and many students, lot of confusion is there about this. So this intensity is about the photon intensity, and this intensity is intensity of light. So many textbooks, they are writing that intensity is proportional to number of photons per second. When I write it like this, area also let us say constant, then E factor is also taken as constant. Note that There have been lot of arguments even with many teachers that intensity is proportional to n by t means what? Now see, if I talk about intensity of light, then here E is a factor which we are taking as constant, E is a factor we are taking as constant. So E and A if you take constant, then this intensity is intensity of light. This is intensity of light. But this is not intensity of light exactly, it is intensity of the photon which is called photon flux. Number of photons crossing per unit area. So let us get the relationship between them. This intensity of light, let us write this intensity of light. And in this intensity of photon, we can exactly get relationship between them. What is that? So you can see that this and Ta, this is what it is intensity of photon. So intensity of light is equal to intensity of photon into E, right? Is what it is. So whenever in photoelectric effect they are talking about, they are clearly talking about this intensity of photon which is called photon flux, and this is given by only this formula, number of number of photons per second per unit area, of course. Okay, so this is the photon flux or intensity of photon. It is not related with this energy. It is not at all related with energy. This is main idea here. So intensity of photon is completely independent, completely independent of energy, of photon. This is the definition of particle. This is the particle definition. Okay. Because generally in the wave definition we have the concept of energy, but in the particle definition of intensity we do not have the concept of energy. That's the main idea behind it. Okay. Right. So I think we have covered the most important concept here. Then we should note photoelectric effect. I think let us carry on this next class. Tomorrow we can cover up further on this topic, right? So today we have discussed about your doubts, whatever your doubts have. We have started this chapter dual nature, and it may get over in the 2 3 classes maximum. Okay, we'll wind up this. So tomorrow we'll try to cover as much as possible. Fine. Let us meet in the next class then. Yeah. Bye bye.